Good evening, ladies and gentlemen. This is Team Entangled Angle, and I'm Nandan Patel, and I'm going to be presenting today's demo on quantum simulation of the 1D Burgers equation. Starting off with the 1D Burgers equation consists of three terms. The first is velocity flow term, a convection term, nonlinear one, and a linear diffusion slash viscous term. The mu parameter on the RHS represents the viscosity of the fluid. We kept the viscosity as mu is equal to 0.1, as it represents an optimal balance between the nonlinear advection and the linear diffusion. The goal of the project is to develop an end-to-end quantum classical pipeline with classical pre and post processing and with a quantum algorithm in between as well. We want to ensure that the boundary constraints are efficiently integrated and the model is scalable and the errors do not accumulate too much. We also have a target goal equation in mind, which we aim to arrive starting from the 1D Burgers equation. Let's see how we do that. We had been given an initial condition as a step function with a step at x is equal to 0.5 and a domain ranging from x is equal to 0 to 1. Now, this is prone to instability and shocks, especially at high Reynolds number regimes. So, therefore, we change the initial condition, keeping the domain the same, but including a sine curve, which smoothens out the entire curve, makes it differentiable, and gives it the ability to absorb shock well. The first part of our methodology is the Kohlhoff transform, which is a mathematical technique used to convert the nonlinear Burgers equation into a linear heat equation. As you can see in the right-hand side of the presentation, you can see the transformation that has been happening from the Burgers equation to the heat equation. The nonlinearity of the Burgers equation has been completely removed, and the implementation for the Kohlhoff transform in our code can also be shown on the right. You can read it as per your understanding and for your reference as well. Now, the second part is the discretization part, and this is a very common part in all the quantum PDE solvers. We discretize the grid into 16 points, and therefore we initialize the Laplacian matrix as a 16 cross 16 dimensional matrix. And following the initial Dirichlet conditions, the matrix is also tridiagonal. We also use a second order difference to get a finite approximation of the wave function, which has been given on the RHS of the 1D heat equation. And the initialization for the Laplacian matrix can also be seen in the code on the right, and you can read it as per your understanding and for your reference. Now you might be asking, how does all of this relate with quantum computing? Well, let's see how. After we discretize the entire wave function, the Laplacian operator can also be discretized into the Laplacian matrix L, and therefore the heat equation now becomes the one that you can see in the screen on the PPT. And if you may remember, this is also the initial goal equation that I had showed to you in one of the initial slides. And for the quantum part of the pipeline, we perform a process called as trotterization, where we basically define and evolve an Hamiltonian over time, and we decompose it into different number of steps, and we get the results at the end. We initialize the Hamiltonian as minus I mu L. Mu and L have already been explained above, and we add an I to make the Hamiltonian Hermitian, and therefore executable on a quantum circuit. The trotterized circuit can be also seen in the code book on the right, and you can see that we have executed an RX6 gate to ensure that the qubits couple well, and the results are also made accordingly. To perform the error mitigation, we use zero noise extrapolation, which is basically running the circuit at different noise levels and then using those to extrapolate it to zero to get an idea of the circuit at that level. And we use the linear model to accomplish the same. We prove that this decreases the circuit depth and N2 errors quite significantly. And the code for the zero noise extrapolation can also be seen on the right. You can read it as per your understanding. Now, for the classical post-processing, we have 16 different wave function points for 16 different grid points, and we kind of sum them all to get the overall wave function psi value. And then we use the inverse Kohlhoff transform to compute the u value given the initial psi value. And this can also be approximated using a second order finite difference method. The transpilation along with the classical post-processing takes place in one code block, and this can be seen in the code on the right. You can see that we have performed the transpilation and the post-processing accordingly. Now, for the classical benchmarking of the code, we have used a classical Krylov-based solver to compare a solution. We have initialized the matrix as mu into N, and we have multiplied it several times by the initial state to get the entire subspace spanned by the vector that is present on your screen in the PPT. And for orthogonalization, we use Langsdorff iterations since the Laplacian matrix L is symmetric, and we get the optimal value of eigenpairs, which we then scale to get the optimal value of U, and which we then compare with the U value, which we have got from the quantum part of the code. For the metrics used, we use three different metrics: L2 errors, dissipation rates, and circuit depth. We have compared the U value for 6 time steps and for 3 different methods: classical method, a noisy quantum method, and an error mitigated quantum method. And you can also see the parameters that we have initialized in our code in the PPT as well. And here are the plots that we have gotten for the implementation of the code. This one is the implementation of the Burgers solution at t equals 0.02. And on the right, you can see a circuit depth code and L2 error code as well. And they both scale linearly with time. They are not exponential or they're not exponential, and therefore can be scalable. All in all, concluding the Kohlhoff transform along with totalization, they preserve the dynamics of the 1D Burgers equation and they remove non-linearity. And this also removes complexity compared to the Madelung transform. And as for future works, we can use a standardized ZNE library for higher time steps and for higher dimensional qubits and the Laplacian matrix as well. And thank you for the presentation. That's all we have.
Thank you, Nandan. Wonderful. Yeah, within time. Perfect. I would now request the judges to see if they have any questions for Nandan, or we'll move to the next presentation.
Nandan, great job. One thing, can you go back to your result slides?
Yeah.
By the way, this is Abhi Chopra from BQP. Do you mind actually putting it in full screen?
Yes, sure.
So that it's not very visible. Okay. So what you are saying essentially is there is a little bit of a deviation in the accuracy for the quantum methods, both the blue and the orange one, which is noisy and all. But can you talk about why do you think this like deviation from the classical comes in?
The main reason for the deviation is the errors basically. The errors, they accumulate too much over time, and the RxX gate that we had used in totalization, it has a habit of that if the time steps are too large, then the errors, they scale exponentially as well sometimes. So although we have used an error mitigating protocol of ZNE, and it does improve the results slightly compared to the noisy quantum protocol, still it is not enough to get it, to get it matched to the classical one, which is deemed to be the accurate one. We could use better standardized error mitigating protocols to execute the same.
Okay. This is very interesting and very good job. Another follow-up question quickly is, you mentioned that instead of Madeline transformation, you have utilized your method. So what specific part? Is it the totalization step that you are talking
No,
about as
no, I'll
the
actually
core?
show you the slide.
Okay.
So in the instead of Madelung transform, we have performed the Kohlhoff transform. So Madelung transform, you basically, if you do the Madelung transform, you get a curl-free wave function, and which is not suitable for fluids with high rotating velocity. And to rectify that limitation, we have to introduce a two-spinor wave function. And to calculate the density and the velocity using the two-spinor wave function is quite a complex process. And so basically, the Madeline transform was infeasible for us in the long term. So the Kohlhoff transform is basically just a short method of ensuring that nonlinearity is removed and the method is not too complex.
Okay. Very good. That's all from my side. Thank you.
Wonderful. Yeah, thank you, Abhishek. Thank you, Nandan. Great presentation. So next up, we have Team Plodinger.
Okay, so hi, my name is James Austin Meyer, and I'm speaking on behalf of Faniza Faz Tahir and Ramachandran Ram Sakanapuram Sirkanth on a hydrodynamic Schrodinger equation approach to solve fluid flow problems that we call flow, short for Flodinger. Okay, so what are we doing and why should you care? We solve classically intractable fluid flow problems, for example, the Burger's equation and potentially the Navier-Stokes equation eventually, via a quantum analog a la Schrodinger and Madelung. The Burger's equation is essentially the Navier-Stokes equation, where we just forget the pressure term and remove the incompressibility constraint. And so if we understand the Burger's equation and solutions to it, we will gain some understanding of, say, the Navier-Stokes equation, and in particular, some sort of lower bounds on the solutions. Okay. So what is the Flodinger approach? Well, we like Burgers, not just any equations. And so what we do is we think of a Schrodinger equation as parametrized by two parameters, say A and M, a la Gross and Padievsky. And these two parameters can be varied in such a way so that when you perform the Madelung transform, you get closer and closer fluid flow problems to the original Burger's equation with its initial and boundary conditions. And so we just perform some sort of classical optimization using a loss function, kind of basic gradient descent. And we push these parameters toward the appropriate parameters to get the appropriate Burger's equation. Okay, just looking in the chat. Okay, no. Yeah, so once we have the appropriate parameters, we take that Schrodinger equation and we regard it as a quantum ansatz, in particular a circuit. And this is the circuit for those who are interested, and I can talk about them more in the questions session if people are curious. We ran some quantum hardware, and we did pretty well. I list a bunch of stuff here for people to read if they're curious. And then we also ran a noisy simulator, and I'll show you the results. So the L2 error reduced as we took more and more steps, which is to say that we got better and better results as we went. And what is kind of curious and kind of interesting, and we couldn't figure out why this happened, is there's this kind of weird periodic spiking, but it eventually seems to level out, which is okay, I guess. The sort of interesting thing is that this seems to be quite scalable. It scales kind of linearly with these like, yeah, the number of these X gates. Right, if you go back for a second, or these well, I guess, yeah, NX things. And so in particular, we're pretty confident that this is the way to approach this problem, right? Like this quantum tensor network approach, I mean, it might be fine for a while, in the sense that like at sort of smaller scales, it might be okay, and hybrid approaches might be okay. But then eventually, like, you want to embed this problem into the quantum realm and just use a quantum computer to solve the problem. So at a certain point, this seems to be the way to go. And so we emphasize this approach in particular because we were most confident with it. And it seems to be working as you would hope. Anyway, so who's next? Well, there's Euler's equation. There's the Navier-Stokes equation, of course. And if we had more time, we would have probably had, an even more, kind of a deep understanding of really what's going on here. And maybe we could even improve on this circuit that I showed you in the previous slide. I think we could probably do better than this. We just had to kind of slap something together for the sake of time. And yeah, I mean, thinking about this more, especially leading up to this, I think we could probably improve on this quite a bit. Anyway, so yeah, there's a lot of stuff to think about. And if we were to be given the opportunity to work with all of you on this project, I'm sure we could make some great strides toward, say, understanding Navier-Stokes, which is really the sort of ultimate goal. Okay, so here is the longest way to spell Finn that you will probably ever see in a presentation. Thank you for listening, and if you have any questions, Rem and Faz are here in the audience to join me to answer them for you. Thank you.
Thank you. Perfect. Thanks a lot, James. Over to the judges for any.
Thank you for the presentation.
Sure.
Quite a good job. Can you go back to your result slide? You mentioned that you have run both hardware and the noisy. So the result that you are showing is with which of the ones?
This result. Yeah, this is using the quantum hardware, like, against the classical solver.
Okay.
That makes sense.
And did you see exactly the same result with the noisy simulator as well?
No, I think
I can take that question.
right.
So,
go ahead.
this is the result from our noiseless simulator. So with noise, we didn't have a proper version of the graph in our slides. So yeah, this is the result from the noiseless simulator. Yeah.
Okay. And for mitigating the noise, you have used any strategy also? Okay.
Yeah, we try to explore ZNE-based noise mitigation strategy, but that was like a basic level of noise mitigation, so we didn't get much, errorless result using that. So we were exploring some other mitigation strategies as well.
Okay. Any other questions from anybody else? If not, just a quick comment on the right-hand side plot. Your y-axis is step. It's more so like time, right? It's showing time. So
Yes.
it is somewhere at the 8th or the 9th step, which is taking like a very high time, and then it's coming back. So it's not the physics behavior, it's a numerical behavior, it seems like.
Okay, you're thinking of some type of something based on the kind of computation structure as opposed to like the actual
Yeah.
physics. Okay.
I don't think so that's physics based because at least what you're showing is time versus the step count. So just a comment there. Thanks for the presentation.
Okay,
Good
yeah,
job.
thank you very much. Yeah, bye.
Wonderful. Thank you, Jim. The next team we have is HSE Solvers team. I would request the speaker to switch on their videos and start the screen share whenever they're ready.
I'm really happy to be here and present our work. First of all, Baker's equation is a canonical model for turbulence. It captures nonlinear steepening and viscous smoothing. It plays an important role in fields of gas dynamics and fluid mechanics. Our work addresses this PDE with a quantum approach. First, we have to map the 1D Berger's equation to the HSE framework. In this framework, no explicit nonlinearity needs to be programmed. The hydrodynamic form recovers it from Schrödinger equation and evolution, actually. We find out that the key challenge is maintaining the normalization, phase estimate correction, actually, and projection back to the divergence-free velocity fields. Yes. The core program consists of 4 main steps. First one is prediction. We simulate the time evolution of the HSE via the trotterizing the Hamiltonian into kinetic and nonlinear components. We do this by applying a QFT, a simple phase rotation, and another inverse QFT. The next step is normalization. We have to project the wave function back to the normalized state. We use a quantum ancilla to measure the total probability. The third step is the phase calculation. We recover the hydrodynamic velocity from the wave function. We do that from the obtaining local phase and approximate phi gradient using finite differences. And the last step is gauge transformation. We have to impose incompressibility by applying a local phase correction. We do that using a position-dependent rotation. And after all, we quantify the differences between the quantum-derived velocity and classical Kohlhoff simulation using L2 error. Now I want to talk about the challenges we faced during our work. First was the simulating nonlinearity with pure quantum circuit using, for example, VQE or similar approaches would cause to the noise sensitivity and the circuit depth. So we choose to simulate our system with a hybrid approach and use a classic in some steps. So we choose nonlinearity over the pure quantum. The circuit, another challenge was the evolution of the circuit was not producing any phase at first, a phase curvature. So quantum potential was purely zero at every step. That would resulted in the simulation evolved purely with the density part, and C naught count was zero, and L2 error was huge. We found out that the viscosity damping was applied too weakly, and we fixed it. And next step was that at the first time, at the beginning of the time and simulation, Q was zero, and we used finite sampling, a tangent smooth step. After all, we ran our code for different parameters using a gradio. The only difference is we find when we change the number of the qubits, and changing the time of the simulation or the change of the steps of the simulation will make no differences. And it's correct if we use the noiseless backend and hardware. If we use the noisy backend, the situation will be different. And that's obvious because we expect from the stable simulation that will not change anything when we change the time of the simulation. Thank you for listening. I hope everything was clear.
Wonderful. Thank you, Fatana. Over to the judges for any questions.
Thank you for great presentation. So I'm just curious, what do you think was the reason in the formulation that could have helped in the last 4 points that you mentioned in your challenge slides? Is it because of some of the transformation you have taken, or is it because of the discretization method? So what did you get a chance to diagnose that part? I think it was slide 5 you were presenting.
I cannot understand your question. Can you explain it more? I'm sorry. I'm really sorry.
So if you go to slide 5.
Slide 5, yes.
So the last 4 points, right? Was that arising due to the transformation part? Was that arising due to the discretization part, or something else? Did you get a chance to diagnose that?
We changed our parameters, and I think it was because of the discretization, and we solve it by decreasing the steps, the time of the steps.
Okay, and not the spatial. So the distance or the spatial
Yes,
that's not
yes,
affecting. It's the time that was affecting.
yes.
Okay, got it. Then there seems to be Kudzai who has raised his hand.
Sorry.
Yeah, I think he would be the speaker for the next team. So.
Oh, I see. Okay. Interesting. Can you go to your results slide? Slide 6.
Yeah, of course. We had 4 qubits. We ran our code for 4 qubits, and this is the differences between the noisy for the result, our result for the noisy backend and for noiseless backend, and the classical state that we had. And this is the L2 error, a difference between the quantum solution and the classical.
Yeah. The interesting part is the noiseless simulator that you tested, which gives a good reference, tells me that something in the method itself needs to improve, but that's a good reference point. Thank you. I appreciate it.
Thank you.
My internet connection is quite unstable. I'm just going to turn on my camera just so you can see me, but giving you that as a heads up. Sorry for that. Okay. Every plane we fly and every field we trust depends on computational dynamics. CFD already cut wind tunnel testing by 70%, saving industry billions. But at shocks and turbulence, classical solvers still struggle with nearly 2/3 of aircraft certification tests still need physical experiments. And scaling is brutal. A modest 3D grid can eat terabytes per time step. That's why we asked, can we map Berger's shocks onto quantum amenable form and actually learn something on today's hardware? Good morning, everyone. We're physics, maths, and optics trio. The first one is Islam, Luis, and myself, Kudzai. And we took the HSC approach to answer this question. The core idea of our solution is a 4-step mapping. We start with the Berger's equation. We move to the Madelin transformation. We evolve psi with a Schrödinger-like HEC that captures diffusion via kinetic phases, and then extract velocity from the phase gradient. On the circuit, that's figure 2. One type of follows the following progression. We start with the QFT. We apply K-squared dependent phase, that's the kinetic evolution. We apply optional gauge or potential. we apply IQFT and then perform a readout, and that forms our HAC primitive. In figure 3, we should also keep it NISC friendly with a tensor network that is an MPS backend. So memory scales at an order of n chi-squared instead of an order of 2 to the power n. And in this case, MPS stands for matrix product states. For our system grid, we use 8 qubits total with a 4-spinner design. And on hardware, we did a demo that simplified it to a 4-qubit variant. So we generated results on a series of dashboards across 27 timestamps. This is an example of one of the results that we had. This is for simulation. We also had something on hardware. This simply shows a comprehensive solution and quantum state analysis across different timestamps. So essentially we did 27 and we were capturing 4 across the duration. So for the results, I'm going to start on the right-hand side with the first row. So in simulation, both the solvers track the exact solution, but the differences show up at the shock. So the classical stays sharp, quantum smoothens at the front, and that's dispersion from the HAC mapping. On hardware, that's the second row, the gap widens, profiles are noisier and deviate more, but the key milestone is clear. The pipeline runs end to end on real qubits, and we can see exactly where error mitigation and scaling are needed. For rows 3 and 4, the gradients reinforce the same story. The classical captures sharper peaks, quantum smoothens them, which is less precise but avoids spurious oscillations. Hardware flattens and the gradients further, but still preserves the shock structure. And then on the left-hand side, we see the error metrics. So the classical FDM holds the lowest L squared across time, and these are the bars that are in blue. The quantum simulation has higher errors, but it is consistent across time. And the hardware has even higher errors, still with fidelity in the 0.5 to 0.8 range, and entropies ranging from about 3.6 to 3.9 bits. The takeaway is that while classical wins in accuracy today, we have demonstrated quantum CFD working end-to-end and highlighted where to push next. So just to push back on that again, the blue bars are the simulation, and then the pink and purple bars are what we did on hardware. On our simulation, quantum HAC solver successfully ran a full 16 by 60 grid time involution, though slower than classical. It still proved the pipeline works from end to end, and on real hardware, we executed about 1,024 shots per snapshot, capturing entropies of about 3.6 to 3.9 bits, and meaningful velocity constructions, even under noise. The promise here is not that quantum beats classical today, but we've shown we can model real fluid shocks on actual bits, and that the first step towards scaling to complex flows that matter for airplanes, cars, and climate. Our future scope is an algorithm we've been testing past the submission date. We were proposing a quaternionic Liouville HAC that we've prototyped. You can see kind of what the pseudocode would look like on the left-hand side. And we've also tested some results. We see they're pretty much comparable to what we find with the FSD, as well as with the simulation, what we found on the hardware. So this is a very promising step we're hoping to pursue further. So we just want to thank WISE and Womanium for the amazing learning experience, and we look forward to the QSL fellowship. Thank you. I'll take questions. Islam is also here for that.
Thank you. Amazing.
Thank you. This is very interesting. So just so that I understand, what you have done is taken the HSC thought process, the transformation from it, but then you have applied the matrix product state to basically solve for it on a quantum system.
Yeah, absolutely. Yeah.
Interesting. Can you go back to your slides on the result, the first slide on the result?
Mm-hmm. This is an example of the dashboards we had, and this is a full summary.
Yeah, slide 6. So in the slide 6, what I'm seeing essentially is, so in the top one, which you say the simulation, that's running on a simulator of some kind,
Yeah.
and that's noiseless simulator, right?
Yeah.
Okay. Okay. So it gives that reference point. I'm not able to fully see it, but it seems the third and the fourth time step has the deviation, whereas the first two time step do not have that. I cannot see what those timestamps are, but
Yeah, absolutely. So the first timestamp is 0.01. Let me see if I can enlarge this
that's
myself.
okay. But it's 0.01. The second one is 0.1.
0.06. And then the third one
0.0.
is 0.15. And then the last one is 0.27. So that's 27 timestamps.
Okay. Okay. Got it. So it seems that the simulator is able to capture at least the behavior. There is some physics element which is coming on the right two plots, right? My
Yeah.
question and my one question which is very, very interesting to see this in this. I'll not look at the hardware result. It's great that you guys got it. It's where we have to go. But the third row gives me a sense that is the Madelung transformation, because when you do that, you do get some additional terms that you might not see in classical fluids. Is that what you are saying? The flattening of the curve is causing by that extra term?
Can you repeat your question again? Sorry.
So when you do like some kind of transformation
Mhm.
of yours, you end up with some additional terms. If you match those
Yeah.
additional terms with HSC with your classical fluid equations,
Mhm.
you're saying that that additional term might be causing some differences in the velocity gradient results?
Yeah, we suspect that that might be the case, but we didn't actually probe further to
Mhm.
test that. But yeah, that's what we suspect.
Interesting. That's a very interesting thought process. Thank you. This is really good work.
Perfect. Thanks, Budzai. The next team we have is QML solvers. The speaker is requested to switch on their video and start screen sharing whenever they're ready.
Yeah. Hello. Vadan, is the screens visible?
Yeah,
Okay.
perfect.
Yeah, I'm ready.
Yeah,
Uh,
please go ahead.
okay. Hello, everyone. I'm Vanshaj on behalf of QML Solvers, presenting our work for the quantum algorithm as a PDE solver for the CFD problem. So before going into the solutions, let's understand quickly why do we need burgers. Uh, CFD is a core part of the aerospace industries and most of the modeling industry, while the underlying equation that governs the solution is defined by the Navier-Stokes equation, which is basically tedious to solve because we have non-linearities and then you have pressure terms and so on and so forth. So for the industry relevance, it's very important to have something that can be used as a testing ground for different algorithms, and that is where the Burger's equation comes in. So Burger's equation provides a simple test bed for analyzing the different effects of fluid flow, and it basically captures the essence of the Navier-Stokes equation. Now, the exact problem statement that we had was we have 1D Burger equation defined by this with the spatial conditions and the temporal domains with the initial conditions and a Dirichlet boundary condition. So the solution that we proposed is basically a comparative analysis. Firstly, because we were a bit new to the quantum algorithm for the CFD, so we approached this as a challenge to understand how the quantum algorithm behave in respect to the other classical methods and let's say the pins approach, because it has been tried. So the idea that we came up with is let's study both the QTN and the HSC algorithm, benchmark it against the classical numerical solvers and then neural network approaches. Identified on the metrics of L2 errors for both the algorithm, the solver accuracy, the stability, and the efficiency. Now, what we aimed for in the approach was let's benchmark. We'll do a comparative analysis, evaluate, and then analyze the behavior of it. Now, the first study that we began was the pin-based approach, where we initialized it with 4 hidden layers with 40 neurons, conducted the learning for 5,000 epochs with a learning rate of 0.001, and this is the result it gets. Then we analyze the different discretization methods because there are a lot of it. You have FDM, FEV, FVM, Fourier, discontinuous Gatlin. So we did not know which one to approach to. So our team members did a very deep analysis on the discretization methods, and here are those plots. Then we went into the core of the quantum algorithm. We implemented both HSE and QTN. For the HSE, we went by the route of Medellin transformation, encoded both the fluid and the phase information on n spatial points. Time evolved it with the tortorized Suzuki approach, encoded the Hamiltonian as with both the kinetic and quantum potential terms, executed it both on the noisy and an idle simulator, and then post-processed it for the wave and for the phase and the velocity term extraction. For the QTN implementation, we basically started with velocity, did amplitude encoding on n spatial grids, made it into a low depth ANSTARs using a two qubit blocks, updated it using an SPA, SA optimization methods, then added basically normalization conditions and mass conservation, ran it on the both the noises and the noiseless simulator, and rescaler to extract the volume, the velocity the velocity fields. So coming to the results now, these are the HSC results for the grid size of N64, the grid size of 8, and an overall graph for the for grid size, the runtime, the QL2 error, the relative quantum and classical error, and the circuit depth. We looked into it closely and saw that since we implemented for finite difference method and spectral, the finite difference performed a bit better in the circuit depth, but for the cases of the runtime, the spectral goes a bit better than the finite difference approaches. And then coming to the QTN results, we had a similar show for both the finite difference and the spectral, where the runtime for the finite difference is again larger than that of the spectral. So we looked into it closely and understood that the spectral is a bit better approach than using finite difference for the QTN and HSC. The overall result for our entire work is summarized in the table, with highly focusing on the accuracy, the strengths, the resource demand, and basically the validations of it. The conclusion from our work is that the wall clock time for classical is still outperforms that of any quantum algorithm that is implemented so far. One, because the 1D approach is still within the limits of the classical solvers. Second, the quantum approaches is basically dependent on the hardware that we have, and it increase the depth of the circuit increases as we increase the number of qubits, so that is a drawback. But within the quantum approaches, the QTN and the HSC, both for small grid points can be implemented on a small hardware. It runs effectively on a Mac Silicon chip. But for a larger number of grid points, for the, let's say for QTN, we took the N as 128. It took around 20 minutes for the system to run. So that is a bit of a drawback there. Overall, we basically saw that the classical algorithms are currently much faster. The quantum algorithm does show proof of concept in scaling, but they incur high runtime and large errors because of one could be that we have not implemented much of the error mitigation techniques. That is one of our future prospect. Another is still that the HSC, while implementing it, has a transformation which adds on much terms. For example, the quantum potential that adds on complexity in the algorithm itself. So that can be another reason where the algorithm is not performing well. So have we met our goals, which we started with? We have done so far good. We have done a detailed analysis of QTN and HSC, both the algorithms. We also compared it with the classical and the neural network, and the code is modular enough that it can be extended to 2D, 3D, and the hardware approaches as well. So for our future scope, the first direct task that we want to do is
One shot, we are a minute over time. I would request you to start wrapping up.
Sure. We want to check our solution with the hardware and extend the noise mitigation techniques in it. Thank you.
Great. Thank you, Vanshaj.
Thank you.
Very good work, Vansaj. Can you go back to your slide where you showcased that you guys looked at all the different discretization methods of finite difference, finite element,
Sure.
spectral? I missed the point of why you selected finite difference and spectral and not the other ones. I
Sure.
cannot see the plots. So can you zoom in a little bit on the right-hand side a little bit?
Sure. Okay.
Okay.
Okay. Let me give me one. I'll show you a table that could make it a much better approach. Can you see these errors?
Mm-hmm.
Okay, so based on this, what we saw that the Chebyshev for our test case for the smooth step, we did not got any result out of it, so we ignored this. For finite different and spectral, the idea is that you have two different. We wanted to have two different kind of discretization method to understand how it performs, how the algorithm performs on both the areas. Finite different method is easier to implement among the three, and the spectral we had is one more area that we wanted to explore, because in that case we basically approached using sine wave and the Gaussian pulse, not by the smooth step. Does that answer the question?
Yeah, no, thanks. I can see why you went that way. It's
Okay.
interesting to see the point that you are mentioning in your plot that the discretization error is lower in finite difference, even though in this case you can sort of see that for sine and the Gaussian pulse, which might or might not represent fully the Berger equation, which is okay.
Correct.
But the spectral method, I will be very curious, and you're right that finite element implementations and even finite volume for that matter, it's not trivial.
Correct.
But very interesting to see that the spectral methods are faster or has faster execution time. I think that's what you are saying from your method.
Correct. That is what we also observed, that in both the HSE and QT, spectral outperforms in the runtime, but the L2 error is a bit higher.
Okay.
Yeah.
Thanks for this. Very good job.
Thank you.
Great. Thank you, Vanshaj.
Thank you.
Next game we have is QTN for CFD. The speaker is requested to switch on their videos and start screen sharing whenever they're ready.
Hello everyone, my name is Nahida Haghani. Today, together with my colleague Bentran, we will present our project on investigation of the one-dimensional viscous Berger equation with Riemann initial condition and Dirichlet boundary condition. The main challenge is in traditional dense solvers become memory intensive and costly at this scale. So this matters because similar issues appear in real-world fluid dynamics and nonlinear partial differential equation. To address this, we use quantum tensor networks. So our objective is to build an efficient solver for the PDE, and while tackling with the computational and memory cost of dense solvers. To this end, we adapt the quantum-inspired tensor network methods and benchmark it. We discretize the solution on a grid of size 2 powered by n instead of storing the full vector, and we approximate it as a chain of low-rank tensors. This reduces storage, and with the TT cross algorithm, we can encode the initial condition directly without forming dense vectors. Okay. Yeah, the special derivatives are discretized with finite difference stencils and encoded as matrix product operators. This operator act efficiently on the matrix product state through local contractions. And the bond dimensions stay small, so we can apply operators without forming larger dense matrices. We started with the dense discretization, which quickly become expensive. In the following steps, we try to address this. In step one is to apply matrix product states and matrix product operators compression to reduce memory. Next step is uses the TT cross to initialize the smooth the Riemann profile directly as a matrix product state. And in step 3, we handle the nonlinear advection term with tensor contraction and truncation to control bond cross. And finally, we built a complete QTN solver and benchmark it. In terms of memory, dense solvers grow exponentially, while matrix product state reduce the memory to polynomial scaling. Each step costs only log n time chi cubic, and a small bond dimension here is efficient, while larger values capture shocks at higher cost. And finally, local MPS and PO contraction are parallelizable, making this approach well suited for high performance computing and quantum inspired implementation. Here I pass the word to my colleague.
Thank you, Nahid. I'm Banchan, and for this project, we did some solution. We developed a classical solution, Ranju-Kuta 45, and quantum inspired quantum tensor network QTN, and the last one, quantum physics informed networks. So we try to compare three solutions. You can see on the slide, we have the results for solution for three solutions, and we have a similar results for three solutions. Next. We benchmark between classical solution, AK45 and PTN, and you can see on the left is L2 error between QTN and AK45. So it increased from 2% to 14%. And we also measure the one clock time between classical solution and quantum inspired solution. And of course, classical solution have a shorter time because QTN has some overhead. Next, please. Regarding to QPIN, it's a quantum version. So we develop solution with a quantum circuit, and we use F8N basis is fit for neural networks encoding, and we change our quantum model. And you can see on the slide, the loss perfect decrease from 4 to nearly 0.5. So in here, we contribute three solution, quantum inspired classical solution, and quantum deep learning network. Next. So if in the future, we will try to extend to quantum real hardware for QTN and introduce a lower bond dimension and explore hybrid QTN and SSE. We also have some limitation, like current framework is classical and quantum inspired. So we try to develop more on quantum hardware. Thank you very much for attending our presentation. Any questions?
Thank you, Nahid. Thank you, Ben. Great presentation.
Very good job, folks. Can you go back to the QPIN versus QTN and RK45 slide?
Sure. I think my it's now stopped. Okay, I'm sharing again.
Yeah. So in here, on what you're showing is RK45 is the classical method, right? You're
Yes.
using that as a reference solution. And then the QPIN, I see that green area which is coming in I think the QTN result. Any thought process, any light that you can shed on that part?
Yes, so you can see on the right screen, a QTN solution have a screen part. So I mean, it's a difference between the classical solution and QTN solution. So I think it's come from when we developed the QTN solution, and we try to measure the results. So it may come from I mean the occur when we measure results from the MSV.
Okay. And just from my understanding, was there a discretization method that you used in this finite difference or something else?
Sorry, could you repeat your question?
So the discretization method, which might be mentioned in one of your previous slides, I just want to see that. What was the discretization? Was there a discretization method? Let me ask from there. Yeah, the finite difference tensor. So that's what so you took the equation, you applied finite difference to it, and then on that you applied MPS and pins and others.
Yes, yes.
Okay, got it. Thank you. Very, very interesting work.
Yeah, thank you much.
Thank you so much for your time.
Wonderful. Okay, so we move on to our last but not the least team, Team Feynman Prodigies. Speaker, whenever you're ready, please go ahead.
Yeah. So hello everyone, and thank you for being here today. And I'm Abdullah, and together with my team Hussein and Tanya, we are excited to share our work on resource lean enhanced partial differential solvers. So we can move on to the next slide. We can move on to the next slide. So let me begin with the challenge we are addressing. So high fidelity CFD is vital for fluid flows, but the fine grids and stiff partial differential equation makes it very computational expensive and hard to scale. To study this, we have vicious-Berger equation. So I think it captures two of the real fluid problems, non-linearity and diffusion, which makes it a very perfect test bed. And why does it matter? Since CFD struggles to scale, quantum methods like tensor networks could step in, which can offer complex states and fast solvers. So we can move on to the next slide. So when we talk about classical approaches, so when we are benchmarking, we have to choose the right classical solver. So if we compare against weak baselines, then quantum advantage is meaningless. So that's why we rely on two of the most trusted approaches in CFD. The first one is the analytical benchmark, which is the exact analytical solution through the Kohl-Hopf transform, which was introduced by Gerald Wittham in his book. And the second method that we used was the finite volume Godunov solver. It is widely used because it can handle shocks and non-linear behavior very reliably. And here you can see in the plot with boundary condition that 0 and 1, the shock wave travels through the domain while viscosity diffuses and smooths the profile. So we can move on to the next slide to talk about the quantum methods. So here we have two quantum methods for quantum tensor networks. So the first one is basically a quantum inspired method, which is based on the reference paper we are given. So the quantum inspired method is basically a classical algorithm which uses quantum techniques and does not use gates. And it applies MPOs to the MPS, and it also has the Euler explicit time stepping. And you can see the shock waves within the plots. And then we have the totalization method built using Qiskit, and it contains several operations which we can apply metrics for the state and Euler time stepping. So we can move on to the next part. So yeah, so when we talk about the benchmarking, all the algorithms here we benchmarked were compared against the exact analytical solution, and each solver requires a different dt and number of time steps to require the solution, and the quantum inspired algorithm was observed to be the slowest in time. So we can move on to the next slide. So we also tested our solution on a real QPU. So the real QPU were lot more noisy than the fake backend. So only one time step was run on the real QPU, while 3 on the fake backend. We use the IQM Garnet QPU for this. ZNE on the fake backend gives a very clear higher improvement than ZNE in the real QPU. And IQM backends are a lot more noisy, so we choose to prefer even having IBM fake backends. So we can move on to the next slide. So yeah, so this is the hydrodynamic Schrodinger equation approaches. So we have implemented the HSE plus quantum tensor network approach, which basically is a classical method using quantum inspired tensor networks like MPS and MPO to simulate the 1D Buzzer equation by mapping a fluid velocity to quantum wavelength function. Then we can move on to the next slide. So we also look into the hybrid quantum classical Buzzer equation solver, which basically maps the problem into a hydrodynamic Schrodinger equation, which is easily simulated by a quantum computer. It implements QFT, which introduces spectral diffusion. So we can move on to the next slide. So yeah, we can move on to the next slide. So we can see the results for HSC over here on real hardware and fake backend. So in contrast to Qt, HSC algorithm was immune to noise, and we were able to get good results with basic error mitigation. We successfully ran a solution on the QPU for 5 steps and fake backend for 3 steps. So we can look at the algorithm comparison next slide, in the next slide. So we have compared all the algorithms as we said before, and HSC was more noise resilient. We have clearly seen that the quantum inspired algorithm and the HSC were the hardest to implement. So we can move on to the next slide. So the success metric for our case was we were able to achieve good results for both QTN and HSC with exponential decrease in resources using log n qubits with a vector length of length n. And we successfully implemented error mitigations like ZN and dynamic decoupling. And the table below shows some of the steps that HSC can be faster, like with an exponential complexity in the classical one. And we can move on to the next slide. So there were some limitations over here, like Cole hop works only for 1D, and due to noise, accuracy decrease a lot in the Qt approach. And for the future scope, we would like to scale it up for 1D and 3D using Carlem and linearization. And we like to use more error correction codes and more advanced technique like variational algorithms. We can move on to the next slide. So yeah, here are the references for our project. And thank you all. We are open to questions. Thank you.
Beautiful. Thanks a lot, Abdullah.
Very interesting work. Can you go back to your the summary slide for all results?
Slide number which slide? Result slide?
Yeah, the result where you have summarized in a table form all the methods.
Okay. Tanya, can you go back just a bit? This one or this one?
This one.
Yeah.
So what? So just so that I understand, you have the analytical, you have the Goodenough FEM, so that's your reference solution.
Yeah.
QTN is QTN inspired QTN tautorization, so that's like HSC plus QTN is what you're saying there?
So basically, Qt tautorization is a pure quantum solver, and it is only like a quantum tensor network approach. So we actually had a different approach, HSC plus QTN, but that was also quantum inspired because I think it takes some concept from the QTN inspired one. Yeah.
Okay, so that's the last one, the hybrid between HSC and QTN.
Yeah, I think the last one is also fully quantum. So the last one is also fully quantum. So we have not compared the HSC and QTN like the combination over here, because I think the HSC plus QTN was not actually having some good results in terms of L2. So we have only added the QTN inspired, the QTN tautorization, and the quantum classical HSC. So basically, the quantum classical HSC is pure quantum. Like pure quantum means there are some classical elements in this, but it can be executed on the quantum hardware, and it's noise resilient and fault tolerant. Yeah. So one good thing about a solution is it captures the shocks very well, the shock waves, and you can see even when you compare it with the classical plots, you will be able to see that it really captures all the. Tanya, can you go back? So when you see the plots, you will be able to understand that it really captures all the characteristic of a true Buzzer equation. Yeah.
Mm-hmm. Okay. Yeah, this one is, so this one you have not mentioned in the
Yeah.
table,
So
right?
this one is we have not mentioned because I think we did not run it on QPU and second because it's quantum inspired. But yeah, and also I think it actually due to some bond. I think that in tensor networks and MPO, MPS there is some related issues with the bond dimension and everything. So I think due to that reason, I think we were not able to get some good accuracy with this. yeah, but it can be scaled up to 1D and 2D. But I think this is a good example that it really shows the Riemann step function if you see, and this is the accurate plot we get basically. So this is very close to the classical results. Yeah, and even if you see the HSC, the quantum classical HSC, Tanya, can you move on to the next slide? So if you see the quantum classical HSC, it also captures the shock wave if you see. So it really captures the time steps as well. Very good, in a very good way. And one important thing I want to mention is even with the grid size increasing, it really works well. Like we actually try to test it out with a lot of grid sizes like up to 256 and it's really scaling well. And even with a less amount of qubit, but the only bad thing about the approach is that the circuit depth is too high. So that is one thing, but it's totally noise resilient. Like we have got some good results basically on the QPU and even with the fake backend.
Okay. Thank you. Very good work.
Okay, yeah, fantastic. Thanks a lot, Abdullah. You could stop sharing your screen. We have come to an end for the presentations for the BQP project. So that's